Hello, this is part 2 of lecture 6. The next diffusion topic is the relationship between the diffusion and temperature. Now, I think that if intuitively you would recognize that as the temperature increases and the atoms are moving around more frequently, that diffusion would be faster. And that's indeed true. As temperature increases, diffusion rate increases. The equation, the original form of the equation is that the diffusivity, D, is equal to some diffusion constant, D sub 0, e to the minus q for diffusion over RT. So Q is the activation energy for a particular solute in a particular solvent. There's a Q value for nickel in iron. There's a different Q value for manganese in iron. Okay, T is absolute temperature in Kelvin. R is the gas constant, 8.31 joules per mole Kelvin. Q has units of joules per mole. So all of the units cancel and taking e to the some number but no units. The units for D0 and D are both meters squared per second. So this is one version of the equation, and it works really well if I'm trying to solve for D. But if I'm trying to solve for Q or temperature, something that's in the exponent, then it's easier for me to use this equation. The natural log of D is the natural log of D0 minus Q over RT. Okay? So there's the two forms of the same equation. So the first kind of problem that we'll see for the relationship between diffusion and temperature is where you only have one unknown. So the terms that are potentially unknown are D0, D, Q, and absolute temperature. And in the first example, you're given 3 of those and just have to calculate the 4th. So for that kind of equation, sometimes it's just easier to use this form of the equation. Some people really just don't like to deal with exponents and powers, and so they prefer to make it linear. But I think for most of you, you'll find this form of the equation simpler when I only have D or D0 as an unknown. So here we got the diffusion coefficient, pre-exponent D0 for zinc into copper is 1.2 times 10 to the negative 4 meters squared per second. So I'm given D0. Activation energy, that's Q, is 131 kilojoules per mole. Now notice if it's given in kilojoules that you need to put it in terms of joules for the units to cancel. Calculate the diffusivity at 400 C. Then that needs to be absolute temperature. So we add 273, and this is 673 C. Okay, I'm sorry, it's 673 Kelvin by adding 273. So D, that's my unknown, is equal to pre-exponent 1.2 times 10 to the negative 4, e to the minus 131,000 divided by 8.31 times t, 673. So that exponent value, I just calculated just that value, everything up in here, this whole thing is negative 23.4. And e to the negative 23.4 power, that's equal to 6.88 times 10 to the negative 11. And the whole thing, d, you should get 8.26 times 10 to the negative 15. And the units are meters squared per second. And I think the next slide is just a place for me to work this problem, which we've just done. Last slide here is just, just to illustrate. Oh, I'm sorry, it's not the last slide. But it ought to be. I'm going to stop with this slide because the following ones are on the next video. But anyway, for the slide here, this table, I'm given these diffusivities for different solutes and different solvents at different temperatures. Just to illustrate my point. So carbon diffusing in FCC iron, it would be 5 times 10 to the negative 15 meters squared per second. And at a higher temperature, the power goes down to 10 to the negative 11. As the negative exponent gets smaller, the value of the number gets bigger. So 3 times 10 to the negative 11 is much bigger than 5 times 10 to the negative 15. So again, it's faster at higher temperature. Now, in reality, carbon can exist in the FCC crystal structure at 1,000. So this is just using the constants to calculate. In reality, at 500, it would be BCC, and at 1,000, it would be FCC. So I think I may have contradicted myself. This would be the value for FCC at 1,000. FCC doesn't exist at 500. And this would be the value for BCC at 500. Notice that there's also a difference between the diffusion rate in FCC versus in BCC. These numbers for BCC are smaller negative numbers. So the diffusion rate, no matter the temperature, is faster in BCC as opposed to FCC. Now these two, carbon is the solute, and that's one of the very, very small atoms that can diffuse interstitially. So this is interstitial. Diffusion, or diffusion of an interstitial impurity atom. The second pair, these are substitutional impurities. Nickel, iron, manganese all have a very similar atomic radius and the same crystal structure. So this is substitutional. We can see that the negative exponent decreases with increasing temperature, and that nickel, at least at 500, diffuses faster than manganese does in iron. Okay, so this is just illustrating what we've just calculated as far as at higher temperature. Well, we'll do that in a moment. At higher temperature, the diffusion rate is decreased. All right, and that I'm going to stop here for this video number 2, because the next slide, let's just make sure of that. Oh, no, we get another example. Okay, I'm not going to stop right yet. We'll do this other example. So here we're given d sub 0 is equal to 6.5 times 10 to the negative 5 meters squared per second. Q is given as 135,000 joules per mole. And the diffusivity is what we're calculating. We know that temperature is 773 K. So D is equal to 6.5 times 10 to the negative 5. Put my units outside here so that you can see where they come from in the answer. E to the negative 135,000 joules per mole divided by R, 8.31 joules per mole second. And temperature is 773 Kelvin. Not joules, this is joules per mole Kelvin. So the kelvins cancel, the joules cancel, the moles cancel, and everything in this exponent has, there's no units. Now that's not always the case. Just know that whatever, that there's nothing that happens to the units by taking the exponent of the power to a power. So let's see, we've got 135,000 divided by 8.31 divided by 773. So the exponent here is negative 21.0. And taking e to the negative 21.0, this is 7.58 times 10 to the negative 10. And multiplying that by d0, you get 4.93 times 10 the negative 14. Okay. All right, that ends part 2 of the lecture 6.